Okay, good afternoon. We'll go on with perturbation theory, except that now we'll look at the degenerate case. Okay, so so what happens when we get two states which have equal energies? Okay, so we have the following situation. We have this H0, and we find out that we have two or more, in general, eigenstates. Okay, so I'm going to call them H alpha 0, okay, and H psi beta 0. Okay, so one of them is this state, the other one is that state, and the states have some energy which let me call E degenerate D 0. Okay, so they both have this energy. Now, one thing that you can see immediately, that this representation is not unique. Okay, because we have, according to this, H0 psi alpha 0 is equal to this degenerate energy 0, H alpha 0, right? But, okay, I have the second one, say psi beta 0, also has the same energy, okay, psi beta 0. But not only that, I can form any linear combination of psi alpha and psi beta. So if I look at psi alpha, some A times psi alpha 0 plus some B times psi beta 0, okay, that is also going to give me the same energy, right? ED 0, okay, because each term here is going to give me an ED 0, and I'm again going to get the same state. Okay, so I can form linear combinations of these two states, and they will also be an eigenstate. Okay, so what will happen is that when I have H0 plus H1, okay, if this H1 that I am adding in as a perturbation is sufficiently different from H0, has different symmetries, etc., then I'm going to get, okay, two different energy states out of this one. So the degeneracy will be broken. So I'm going to get two different energy states, okay? So this ED0 is the original level, but I'm going to get first order corrections, which are going to be ED1 and in general ED2, okay, two first order corrections which are going to be different to this zeroth order energy, okay, and the eigenstates that I have here will be okay, different for both of them. Now, to find out what the energy states are going to be, okay, remember the non-degenerate case. In the non-degenerate case, if we started out with the zeroth order wave functions, we could find these first order, okay, so I should say one, right? There are two different types of ED1, so I need some other type of notation, ED1 and ED2, I guess. Okay, so it was sufficient to use the zeroth order wave functions to get the corrections to the energy, right? So here, again, it's going to be the same thing. I'll just need the 0th order wave functions, but okay, those wave functions will be different depending on what H1 is. Okay, so depending on H1, I have to find the proper set of eigenfunctions which will give me these two energies, the first order correction to these energies. Okay, let's start doing let's go through the procedure, and I hope things will be clear in a moment. Okay, so I'm going to define my 0th order, degenerate wave function as some linear combination, just like I did there, of psi alpha 0 and b psi beta 0. Okay, so it's going to be a linear combination of these things. Which linear combination it is, we'll have to find out.
Okay.
Yes?
There was such cases in the non-degenerate perturbation theory that first order correction was 0. There was no first order correction to energy. Is it?
Yeah, it is possible. Well, it's possible here also. Okay, if H1 doesn't contain any, it's the opposite way. For certain H1, you'll have to go to second order in perturbation theory to get a change in the energy, whether it's degenerate or non-degenerate. Okay, but for degenerate perturbation theory, we'll not really go into second order. Okay, so I have this for my degenerate wave function, 0th order, some combination of these two wave functions that I have found. Now, what I'm going to do is I'm going to just write down this equation, H0 plus H1, operating on this psi d0 plus psi d1 in general. Okay, plus higher order terms is equal to ed0 plus ed1 higher order terms. Okay, again psi d0 plus psi d1 and so on. Okay, so that's our equation that we need to solve. We have H0 plus H1, and then this thing just generates higher orders of energy and also wave function. So what's the first order equation? Remember, I combine terms here which add up to first order in the superscript here. H0 psi d1 plus H1 psi d0. Okay, so those are the only first order terms on the left hand side. And on the right hand side, I'm going to get ed0 psi d1 plus ed1 psi d0. Okay, everything else is higher order. Okay, well, there's also the 0th order, but I did not write that down. 0th order equation is right over there. Okay, H0 psi d0 is equal to ed0 psi d0. Okay, that's the original equation, and H1 is just equal to 0. Okay, so I have this equation. Now, what I'm going to do is I'm going to take this whole equation, just like what we did for the non-degenerate case, except that here now I have the two non-degenerate states hidden inside psi d0. So first I'll take this whole equation and find the inner product of that kit with psi alpha 0. Okay, one of the eigenstates that I have started out with. Okay, so what does that do? So this first term here is going to be, let me just write it out, psi alpha 0, h 0, psi d 1. Okay, so let me write everything. Psi alpha 0, h 1, psi d 0 is equal to ed0, which is just a constant. Okay, psi alpha 0, psi d1, and finally plus ed1 psi alpha 0, psi d0. Okay, so now you'll help me out with finding out what these things are. Okay, psi 0, h0 operating towards the left. Okay, I have what that is. Okay, it's going to be, this term is going to give me e d0 and inner product of psi alpha 0 with psi d1, right? Okay, what about over here? Well, psi d has really two terms in it, right? It has a psi alpha 0 and a psi beta 0, and there's an h1 in between. So it's going to give me actually two different matrix elements of h1, right? Okay, there will be one term here, which is a times psi alpha 0. So that's going to give me plus a h1 alpha alpha, right? From the left I hit with alpha, from the right I hit with alpha. But there's another one in psi d0. So that's going to be plus b h first order. Which matrix element?
Alpha beta.
Alpha beta, very good. And then I have here a term which is actually exactly the same as that, so I'll just keep it there because that's just going to cancel. Psi alpha 0, psi d1. Okay. And then this is what? Inner product of psi alpha 0 with psi d0.
Psi d0, 0.
Careful.
No. A.
A, right? Okay. E d1 times A. Okay, so you see that this term and that term are the same, so I cancel those. Okay, so I have an equation like this. Now what we'll do is we are going to repeat this process, except that instead of psi alpha here, I'm going to have a psi beta. Okay, so what happens if I put a psi beta here? Well, you can sort of guess what will happen. There will be a term here which will be psi beta, hd1 psi beta, so those things will cancel again. So there will be a change here and a change there. Okay, so if I replace psi alpha here with psi beta, what do I get?
This one, beta alpha.
Okay, what do I have here?
A,
A,
H1, beta alpha,
H1 beta alpha plus
H1 beta
B, okay, H1 beta beta equals what?
E1 dB.
Okay, ED1 B. Now you see what we get. Okay, we get something very nice. Okay, so that nice thing I'll try to squeeze here. We'll write it again and again, so that's okay. So I have this matrix, which is H alpha alpha 1, H alpha beta 1, H beta alpha 1, H beta beta 1, okay, multiplied by A and B is equal to E D1 A B. So it turns into an eigenvalue equation, and the eigenvalue is going to be the shift in the energy. And since it's a two-dimensional object, I'll get two eigenvalues, right? One of them will give me the shift for one of those energies. The other one will give me the shift for the other energy, okay? And it also gives me the A and B, which A and B I'm going to use. Okay, so if I use those A and B's, I am going to get wave functions, okay, psi alpha and psi beta, which are associated with those eigenvalues. Okay, so for the first eigenvalue, I'll get some A and B. For the second eigenvalue, I'll get some other A and B, which means that for the first eigenvalue, I am going to get one wave function, which is going to be psi alpha. For the other one, I'm going to get the psi beta, okay? And those will give me the energies. Okay, so that's in fact it, okay? So that's all we'll do for the perturbation theory. We'll just look at the first order change. You can go ahead and do the second order change also, but usually, okay, we'll not need that, so I'll not go into that. Okay, so let's just do an example. Okay, so let's create a problem in which we have some degenerate states. Okay, so, and that will be particle in a box. Okay, so suppose I have a box, a cubic box, and I'm going to put it at the origin so that I have this X, Y, and Z coordinates. It's A by A by A, okay, so it's a cubit size A. Yes?
You said that perturbations will be different for two states, but can they also be the same for all perturbations like higher orders too?
Yes, it could be, okay, it could be the same.
If it turns out same, how do you, for example, know if you have a degenerate state or...
No, if the energies are the same, then of course your system is degenerate. Now, you may have a perturbation which may not be able to lift that degeneracy, but okay, then that's life, okay? You need some other type of...
What I mean is that, assume that you know the energies, how do you know whether your energy having the degenerate state or a single state? Like whether if there are multiple states in that energy or just a single state?
Well, you'll have different wave functions, right? Okay, for example, for this problem that we have, you know that you are going to get degenerate states, right? Because it depends on the indices associated with various things. Let's go ahead with this problem because I think that will answer your question. Okay, so I have something like this. My psi, okay, is going to depend on three different n's, okay? So let me call them nx, ny, and z. And there will be a normalization factor here, which is going to be 2 over a square root, but there are three of them, so 3 over 2. And I have sine and x pi over a, okay, sine and y pi over a, and sine and z pi over a, right? So those are the wave functions, and the corresponding energies are E and X and Y and Z is what? H bar squared over 2m a squared, and then there's a pi squared in the numerator, and you have an x squared plus n y squared plus n z squared, right? So those are the energies. Now, there will be a ground state. So the ground state is going to be psi 111, okay? And its energy is going to be equal to that thing there, h bar squared pi squared or 2m a squared, and 111 means I'll get a factor 3, okay? But then there is also a set of first excited states, okay? So, for example, I'm going to get 1, 1, 2, psi 1, 2, 1, and psi 2, 1, 1, okay? So all three of these things are going to have the same energy, which is going to be h bar squared pi squared over 2m a squared times what? 6, right? Because 1 squared plus 1 squared plus 2 squared. So this energy level is now threefold degenerate, okay? So we know now that there are three states which have that energy, okay? Now if you go higher up, you are going to get, obviously, more degeneracies, etc., depending on what ends that you put in. Okay, but let's now work on this state, okay? So the lowest energy state here is E111, and then there is a threefold degenerate state here, which is, okay, E211, okay, E121, and E112, okay? So all these things have the same energy. Now I'm going to put in an H1, which will break this symmetry. Obviously, I can put in an H1 which doesn't break this symmetry, but then, of course, we are will not be able to use the methodology that we learned. So one trivial H1, for example, that I can put in, which will not break this symmetry, is something like a constant potential. If I put a constant potential, okay, everything will increase by the same constant amount, and the degeneracies will stay. In fact, if you put in something like, for example, a constant electric field, again, the degeneracy will not be lifted, okay? If you just put something like X, for example, as a potential. Okay, why? We discussed that earlier. That will result in the polarization of the system. The X coordinate will change, but the energy will be proportional to electric field times the polarization, so it will come in second order. So first order, that something like that will not make a change. But let's look at some H1, okay, which looks like this. So suppose I have an H1 which has alpha times X times Y, okay, something which has this form. Now, what I want to do now is to form this matrix, okay, between all these wave functions, okay? So I want something like H alpha alpha, H alpha beta, except that this time I have three of these things. So I'm going to get a 3 by 3 matrix. So let's just look at the form of the matrix. I'm going to get something like 1, 1, 2, okay, so that's one state. Okay, one of the psi 0 states, 1, 2, 1, and 2, 1, 1. So these are the unperturbed states which are degenerate. Okay? So let me put them on the left-hand side also. Okay, 1, 1, 2, same order. 1, 2, 1, 2, 1, 1. Okay, so those are going to be, okay, so I'll put H1 between them. Okay, I'll put I'll sandwich H1 between them, and I'll try to find out what the result is going to be. Okay, so what will I get? Okay, let me just see. It might be better to put the origin in the center, right? So that I can use the symmetry. Okay, in any case, let's just go on. Okay, so what I'll do is okay, I'm just thinking whether I should move the origin now before I go any further so that I get nice symmetric wave functions. X, yeah, I'll do that. Okay, so sorry about that. Let me go back over here. Yes.
X eksi A bölü 2 desek, X eksi A bölü 2, Y eksi A bölü 2 desek daha
Yes, okay, so that's what I'm going to do. Okay, so that's exactly what I'm going to do. I'm just going to shift my origin, okay, so that it is in the center here. Okay, so it's X and Y and Z. Okay, so that means the n equal to 1 states are going to be cosines, and n equal to 2 will be a sine function and things of that sort. Okay.
Changing the first Hamiltonian while keeping the coordinates change would have been easier for us.
Well, let's do what's easier for me. Okay. Okay. So I have this 1, 1, 2, 1, 1, 2, and I'm just going to look at terms which have, for example, 1, okay, something, I don't know what they are, okay, but I have alpha xy, my h1, and 1 something, okay? So what will that give me? Okay, that will give me,
0.
okay, 0. Why? Because this is just going to be a cosine function. This will be a cosine function. There's an x in between, okay, for the x. In fact, I'm doing something like finding the expectation value of x. Okay, so that's going to give me 0. Okay, so anything that has 1 and 1, okay, 0, 0, 0, 0.
Anything that has 2 and 2 is also 0.
Okay, so if I have also something to something, alpha x, y, like this, x to x is also 0, because now I am finding the average value of y, which is also 0. So, okay, 2 in the center, but I have already taken care of those things, right?
Also 2, 1, 1 and 2, 1,
Okay,
1.
let's see. Okay, let me just make sure we are covering everything. Okay, and what else? 2 and 2, this point, what is that? 2 something alpha x y, okay, and 2 something is equal to 0 again, right? Because now I'm finding the expectation value of x in the second state, so that's going to give me a 0 here. All right, what else?
122 and 211 are also 0 because there is nothing in that direction, and 2 and 1 are orthogonal.
Okay, so what we are saying is that this is 0, right? 2 and 1 is orthogonal in the z direction, so that's 0. This has to be Hermitian, so that has to be 0 also. So I have just these two elements which are going to be non-zeros. Okay, so in fact, let's just look at what those things are. Okay, so this is something which looks like 1, so it's going to be cosine pi over a x, right? And there's an 2 here, so it's going to be sine 2 pi over a y. I'm not going to write even the z direction because they are just both 1 and 1. Okay, so, and in the middle I have an x and y, and then alpha. And on the right-hand side, I have sine 2 pi over a x and cosine pi over a y dx dy. And there will be normalization also, right? So you see, if you look at the x integral, okay, cosine is even, sine is odd, but I also have an x here, so it's going to be even times even, so it's going to be something finite. Not only that, but the y integral is exactly the same, okay, except that cosine is on the right and sine is on the left. So this is going to be equal to some, okay, alpha times this integral squared, where this integral is just one of these things. Okay, so it's going to be cosine pi over a x, x sine 2 pi over a x dx. Okay, and there will be a normalization, which is going to be 2 over a. Okay, so that's our integral, and that will give me this full integral. Let me just give this a name. Okay, let me give this a name, something like c. Okay, so it's going to be the same whether I look over here or over there. Right, it's just the Hermitian adjoint of the other. Okay, so that's my matrix now. And I have to find its eigenvalues and eigenvectors. Okay, and from that I can determine what the how much the shift is going to be in the energies and such things. Okay, so let's just look at this matrix. Okay, so now that you have some amount of experience with matrices, perhaps it's time that we look at certain tricks and shortcuts in determining these eigenvalues.
Its eigenvalues are 0, psi, and minus psi.
Okay, very good. So now we'll verify that. Okay, so we have this matrix 0, 0, 0. Okay, 0, 0, C. Okay, 0, C, 0. Okay, one thing that I can notice is that it's in some sort of block diagonal form, right? So if I just look at this like that, you see there's everything is inside these blocks. This is 0, but that's okay. Okay, it's still in block diagonal form. So that means I'll get one eigenvalue here and two eigenvalues from this matrix. The eigenvalue here is trivial, right? So if I just have 1, 0, 0, that's just going to give me 0 times 1, 0, 0. Okay, so that's one of the eigenvalues. Okay, because it's in block diagonal form. I have a matrix here, Okay, do you recognize that matrix?
Yes.
I mean,
Pauli spin matrix.
okay, it's one of the Pauli spin matrices. So this thing here, 0, C, C0, is just C times 0, 1, 1, 0, which this guy was, remember, sigma x. So I know that it has eigenvalue plus 1 and minus 1. So the whole thing is going to have eigenvalue plus xc or minus xc, right? So, and I know what the eigenvectors are. Those are the eigenvectors of psi of sigma x, right? So one eigenvector will be 1, 1 times 1 over root 2, and other one will be 1 over root 2 times 1 minus 1, right? So these are the, remember, the x up and x down eigenvectors, okay? So this is one, so let's list the eigenvalues and eigenvectors. So the eigenvector value 0, okay, has an eigenvector. So this is really something like psi alpha 0 corresponding to that eigenvalue is going to be 1, 0, 0. There will be another eigenvalue, C, which is going to have, okay,
1 over root 2.
okay, so 1 over root 2 for normalization, 0, 1, 1, right? I just have this, okay, because it's eigenvalue of this block. Eigenvalue and eigenvector of that block. Now I have another eigenvalue which is going to be minus c, right? So that's going to be minus c, and that will be 1 over root 2, 0, 1, minus 1. Okay? So those are the three eigenvectors of our equation. So that means now I have found out what the first order corrections to the energy are. Yes?
Why you divide the matrix into two pieces?
Okay, because if I can, okay, so the question is why do I use, okay, recognize this block diagonal form. If I can put my matrix into this block diagonal form, the eigenvalues and eigenvectors are eigenvalues and eigenvectors of these blocks. Okay, so if I have something like this, for example, I have some matrix M1 and, okay, another matrix M2 here, okay, and zeros over there. So you see, I can easily say that if I know the eigenvectors of M1, I can just write this as M1, 0, 0, M2, and eigenvector of M1, whatever it is, psi 1, 0, is equal to lambda 1, psi 1, 0, right? So it's going to be that. So it makes my life a little easier. Instead of working with a 3 by 3 matrix, here I have a 1 by 1 matrix, but in this case it's trivial, it's just 0, so its eigenvalue is 0. Okay, so that is going to correspond to an eigenvector which looks like 1. Okay, this psi 1 is now 1, multiplying that. And zeros, okay, is equal to 0 times the eigenvector. Okay, so that takes care of that part. And then I can look at the eigenvectors of M2, okay, by, okay, just, okay, I don't know if I can squeeze it here, but, okay, so I have something here which I don't care about, zeros, zeros, and M2, and then 0, some psi 2 here is going to be equal to lambda 2, okay, 0, psi 2. Okay, so I can find the eigenvectors of M2 and they will come into the full picture like this. Okay, so it's just a trick, okay, to simplify the algebra. Otherwise, you have to write a, okay, 3, put minus lambdas in the diagonal, find the determinant, get a third degree polynomial, and find its roots. And when you do that, you are going to get these same eigenvalues anyway.
That
Okay.
polynomial is x times x squared minus psi squared.
Very good, but fortunately we don't need it now. Okay, so where are we? Let's go back to our problem. We found 3 eigenvalues, so let me just leave this in the corner. We found 3 eigenvectors and 3 eigenvalues. So where was my picture? So now I have these 3 eigenstates. Remember, these are the 2, 1, 1 type of states. This was the 1, 1, 1. It's, okay, it's the ground state and non-degenerate. But now I have those 3 states. And I constructed them out of these 1, 1, 2, 1, 2, 1, and 2, 1, 1 states, right? So these coefficients that I find now are associated with that. Okay, so these are the H0 eigenstates. So they are the E0 eigenstates. And I have one which is not going to change its energy because its eigenvalue is 0. Okay, so when I have H0 plus H1, okay, I'm going to get new energies. What will be the first order change in 1, 1, 1? That's non-degenerate, but we can guess what it will be from the form of H1.
0, probably.
Well, I want a different answer, not a probable one.
Yes, it will be 0.
Okay, it's just the expectation value of x times the expectation value of y, right, in the ground state, so it's going to be 0. Okay, so there will be no change in the 1, 1, 1 state. Okay, so that's going to stay the same. One of my states, again, is not going to have any change in energy. That's this one with eigenvalue 0. Okay, so let's choose it as this one. But I know the wave function which is associated with it. Okay, it has a coefficient A, B, C. Okay, so it is made up completely of the first object here. So it's 1, 1, 2. Okay, so this is just the 1, 1, 2 state that I started out with. There will be one state which is going to have an energy which is higher by this variable c, and it's going to have a wave function associated with it, which is going to be 1 over root 2, second one plus the third one. Okay, so this one is going to be 1 over root 2, okay, 1, 2, 1 plus 2, 1, 1. Okay, and finally there is one more which is down by c, okay, lower by that, and that has a wave function 1 over root 2, okay, the difference of the two wave functions, so 1, 2, 1 minus 2, 1, 1. Okay, so you see these 3 are orthogonal to one another, but over here before H1 comes in, I really cannot have any preference over any one of these wave functions. Okay, so over here I started out with whatever these things are. Okay, 1, 1, 2, 1, 2, 1, and 2, 1, 1. Okay, so these are the three degenerate wave functions in some order. But now you see when this perturbation is turned on, so as I slowly increase alpha, so in some sense this is a function of alpha, so if this is 0 and function of alpha, this is customarily how this is drawn. So if alpha is 0, alpha is the coefficient in front of h1, I have the 0th order energies, and then there's this change which implies that the energy is either going up or down or stays the same, okay, as alpha is increased. Okay, so this H1 lifts the degeneracy. Okay, that's what we mean by lifting of the degeneracy. The degeneracy is now, these levels are now split due to the effect of this H1. Any questions? Yes.
Does this H1 also restrict the probability amplitudes of the energy levels? Because it seems like it does.
No, actually these are, okay, so these objects here are just eigenstates. Okay, so this is what I would call, for example, something like psi degenerate, again to 0th order, but for the first object. This one perhaps is equal to psi degenerate second state, and this one I would call psi degenerate 3, okay, third one. It really doesn't matter whether you use these things or those things to represent your state. Okay, they are all three are okay, orthogonal states which cover the degenerate set of energies when you don't have any H1. So you could have the particle in this state or that state or that state with any probability, okay, between 0 and 1, obviously. Yes.
Actually, I was going to ask my first question again. It might be unrelated, but for example, let's say you are in a lab and you observe some energy levels and you don't know about the states, and you apply different fields and you cannot lift up the degeneracy if there is. But can you say after trying every field, these are non-degenerate? Is there another property that you can look into, say something about degeneracy, or is it just energy differences?
Well, it's basically just energy differences, but the degeneracy usually arises from some symmetry, right? So we have threefold symmetry here because we have a cubic box, okay, same dimensions in x and y and z. Okay, so that threefold degeneracy results in threefold degeneracy here. Okay, so from a theoretical point of view, you know that there is this XYZ degeneracy, and we are lifting that by breaking that symmetry. Okay, so we are putting here this H1, which is not symmetric in X, Y, and Z, so it just breaks it up. So whenever you have a degeneracy in a physical system, it's the result of some symmetry. Okay. So you can lift that degeneracy by breaking that symmetry in H1. Okay, so that's how you do it theoretically. But if you are doing an experiment, of course, you can then look at how these levels are getting split when you apply some field, which again breaks the symmetry. Okay, so you apply some electric field or something, and then as a result of that field, you have this splitting up. then you understand that, well, okay, that degeneracy that you have just broken must be related with the symmetry that you have broken by applying a field or something. Okay.
So then it's determined like if you cannot break up the symmetry anymore, like the problem is that how you can know whether you have split up the levels enough? How you can understand that? Maybe you can split up more, but you don't know how.
Okay, so you are asking whether you can have an energy level which may have some hidden symmetry in it it's unlikely that you'll encounter something like that because ordinarily you just apply some field and the symmetry is broken. Okay, so you have lots of fields available to you. Okay, electric field, magnetic field. If you have a symmetry associated with, for example, the geometry, you can compress it so that the box changes its size and everything. So usually there is some field which you can break it up. So the question you are asking is very hypothetical. I cannot really associate it with any realistic.
Properties energy that you can look into. So I'm trying to ask that there isn't any other property that you can look for that, right?
Okay. Well, if you then the problem is what other measurements can you do on the system? Okay, so that involves another operator. Okay. If you are making another measurement. So if that operator commutes with the Hamiltonian, then they'll have the same, they'll share the same eigenstates, okay? But they may have different eigenvalues, obviously. That's why measurement is good. If you carry out a measurement, even if the measurement operator may commute with the Hamiltonian so that the energy states are the same, you may get a different measurement, different value of measurement, because, okay, the eigenvalues of the measurement may be different. Although the Hamiltonian eigenvalues will be the same, the measurement eigenvalues may be different, in which case, okay, you again understand that the measurement is breaking the symmetry.
Can I ask just one last question?
Sure.
So then, can you state that all of our analysis for the Hamiltonian and perturbation can be applied to other operators?
Yes.
Yes. Yes.
I have a question about this.
Okay.
After this perturbation, we still have symmetry with interchange in x and y axes, but there's no degeneracy anymore.
Okay.
But we still have symmetry. So is there degeneracy in, for example, higher energy states, etc.?
Probably you are going to have an effect of that in some sort of operator.
Oh.
Okay.
And for example, if I took a rectangular box with this side in the cube, with this side having length 4 and this side having length 1, then it still has degenerate energy eigenstates. But it is not symmetric anymore.
Okay, so that's an accidental degeneracy. You have something that has occurred because of some sort of degeneracy and accident, okay, just fortuitous, and it's again possible to break it by applying a field, or you just apply pressure and change one of the sides a little bit, okay?
So not all degeneracies come from asymmetry.
Well, okay, yes, there can be some accidental degeneracies, okay, just coincidental. Okay, I'll let you go and we'll meet Friday, I guess.